Okay, thank you everybody for attending our webinar. This is Vikram with GL Communications. I'm joined on this webinar by our senior engineer, Shashi Murthy, and also our sales director from Bangalore, India, Sanjeev. The topic of today's webinar is our ability to test T1 and E1 networks as well as VF and serial data networks. And we can test them in a variety of ways. We can monitor these networks and we can emulate traffic traversing these networks. So that's what we will be talking about today. Before we dive into the subject matter, just a quick overview of who we are. I think a lot of you are familiar with our company, but in case you are not, we are GL Communications. We are located in Gaithersburg, Maryland, United States. That's our headquarters. We also have a development office in Bangalore, India. And we also have sales representatives all around the world. We have been around for over 35 years now. We were founded in 1986, and we do a variety of different things. We're a telecommunications consulting company. We manufacture test and measurement equipment for telecommunications networks, all different types of networks, including T1, E1, your public switch telephone network, next generation Ethernet IP networks, wireless networks, 3G, 4G, 5G networks, fiber optic networks like SONET and SDH, land mobile radio. We have equipment that can test all of these various networks. In a variety of ways, we can analyze traffic on these networks, we can monitor the traffic, we can store the traffic, visualize the traffic, emulate on traffic on these networks, and so forth. So no matter what type of network you are trying to test, I guarantee we have a solution for you. Legacy networks, and when I say legacy networks, I'm talking about your analog phone networks, the plain old telephone system, POTS, public switch telephone network, which is analog based. It can also mean digital networks, but like T1, E1, T3, E3, serial networks like Datacom, and so forth. These networks, basically, when I say legacy, I'm referring to any network before the advent of Ethernet and IP networks. So these networks, these legacy networks, are still being used quite a bit. A lot of customers come to us asking for testing solutions for these types of networks. So why is that? Why are these legacy networks still being used around the world? First off, it's very hard to transition away from these networks once they've been built and deployed. It takes a lot of time and energy and effort and money in order to strip out all of that communications infrastructure, and therefore it's very hard to transition away from these types of networks. Also, these networks are very reliable. Anytime you pick up a call on the old public switch telephone network, you get very good voice quality, and it's a pretty reliable network. You can pretty much pick up the phone and place a call, answer a call, and it's a very reliable network. So these networks are already there, they're already in place, they're reliable, they're available, but they have obvious disadvantages as well. These networks are slow, and because they're legacy networks, they're low bandwidth, and also they're starting to become a knowledge gap with engineers. A lot of engineers that we talk to are not knowledgeable about the old analog telephone network or T1, E1, T3, E3 networks, Datacom networks, RS-232 and so V.35 and so forth. Engineers aren't really familiar with these networks anymore because Ethernet has become so prevalent, and cellular networks like 3G, 4G, 5G networks have become so prevalent. So there's a lot of disadvantages to these legacy networks. The industry needs very easy to use test equipment for these types of legacy networks. And that's where we come in. GL Communications has been supplying test and measurement equipment for these legacy networks for a very long time, an experienced player in this industry. The main product, one of our best-selling products to test the legacy networks, is our tProbe. That's what we call it, the tProbe. This image is not drawn to scale. The tProbe is pretty small. You can hold it in one hand. I'm showing you both the front and back panels. It is customizable in terms of what interfaces are present, but there's a couple key features I want to get across. First off, like all of our test equipment, it's controlled by a Windows PC through a USB connection. We always provide the USB cable. You simply plug it into your Windows PC. We also supply all the software on a USB drive, and you can simply invoke the software and fully control the hardware from a very nice, easy to use graphical user interface. So the tProbe itself has many different ports, as you can see on it. It's got 2 T1 or E1 ports. It's got Datacom ports that can simulate both a DCE or a DTE device. It's got FXS and FXO ports, so it can simulate an analog phone or a wall jack. It has VF ports, 2 VF ports, one here and one here. So those are, your basic input-output for audio. And those are basically the main ports that are supported on the tProbe. When you order the tProbe, you may not need all these various interfaces. Maybe you just need the T1 ports. So in that case, we can always reduce the price and ship the tProbe without the FXO and FXS ports and without the Datacom ports and so forth. So the bottom line is that this tProbe, it's a very small box, but it can have all these different interfaces to test legacy networks. On the previous slide, we showed the tProbe connected to a Windows PC, just a simple laptop. But often customers like us to provide a complete solution. So they want the tProbe and a computer for controlling the tProbe all in one. So that's what this picture on the bottom right is showing you. We've actually placed a single board computer in the same chassis as the tProbe. This is like the front panel on the bottom left here. And this is very nice because it's still actually portable. You can put this in a backpack, but it's also got the controlling computer. So the computer is a single board computer. It's got HDMI ports, USB ports, so you can plug in a monitor, mouse, and keyboard. It's also got an Ethernet port down here, so you can remote into this PC. So whether you need to remotely access the device or locally access the device, you can do so through these HDMI, USB, and Ethernet ports. Now, we can also give you a rack-mountable form factor. So that's what this graphic is here on the top right. We're showing both the front panel and the back panel. And again, the USB connection is in the bottom right here. And again, this is rack mountable. It's 1U, 19 inches, and so forth. So it's very easy to rack mount this. And so if you need to deploy this in a network room, you can do so. So basically, what we're trying to convey here is that no matter what form factor you need, whether you need a portable solution, whether you need a rack mountable solution, we can provide it. Whether you need us to supply the computer, whether you will use your own computer, again, we can provide it. So again, we can ship this rack mountable solution with or without the PC embedded. Now let's talk about the main features of the tProbe. So I already talked about all the various interfaces that it supports. What can it actually do for you? Well, it can do a lot of stuff. First off, it can do fundamental bit error rate testing. So if you're talking T1 or E1, you can inject traffic into all time slots traversing the T1 or E1 network. You can send bit patterns on each time slot. You can send tones, digits, audio files. It's all customizable over all of the different time slots in the T1 or E1 path. You can also do much more advanced testing. You can emulate and monitor a lot of the key telecom protocols, such as ISDN, SS7, CAS. The FAA uses SS1, so we have that as well. If we're talking, we can also do HDLC, frame relay, GSM. So we can emulate these protocols and we can monitor these protocols. And we'll show you some snapshots later in this broadcast about what that all looks like. We can record and play back traffic from the network. Again, we've got a really easy to use graphical user interface. We also support Python scripting, so this has become a major feature for us. A lot of customers have requested this. We now support Python scripting for remote operation and automation. Anything you can do through the graphical user interface, you can also do through a Python script. So we'll talk about that briefly at the end. We can do pulse shape analysis, jitter, delay measurements. We can do intrusive and non-intrusive analysis. For Datacom, we can either be the DTE or the DCE. And we have VF drop and insert capabilities, which Shashi will talk about shortly. The GUI it's very easy to pull up the GUI, view the different T1, E1 ports, view different statistics, and for each port on the tProbe, you can change the configuration independently. You can put it in terminate mode, monitor mode, bridge mode, and so forth. You can use an internal clock or you can use an external clock for the timing and synchronization. It gives you fundamental statistics on the T1 and E1 ports and so forth. So the main GUI, it's very easy to just quickly view all the ports. If you have any errors, it'll show right up, very clear what the errors are, and so forth. Okay, so at this point, I'm going to turn it over to Shashi. She'll go into a little bit more depth upon how the tProbe works and what it can do for you. Shashi, feel free to start.
Thank you, Vikram. This is Shashi Murthy. In the previous slide, you saw the configuration for T1 ports. That cross port has 3 different options. One is normal, other one is cross port through, and the other one is cross port transmit. If it is in normal mode, there is no cross port. But in the cross port through mode, data is passed through and monitored. Data received on port 1 is transmitted out through port 2, and data received on port 2 is transmitted out through port 1. This is used for inline monitoring without touching any data. The other one is cross-port transmit. In this, received data is not look back. We can use error insertion application to look back data and also insert error and delay emulating T1 networks. This is the monitor window. We see a lot of green check marks. Green check marks means the line is up, and if the line is down, it will be red cross. And the statistics shows received frequency, level, received level, errors, all kinds of errors, BPV, out of frame errors, and clock slips. This is a nice oscilloscope display and spectral display. Oscilloscope display, it visually assess activities on the channel such as noise, tone, speech, etc. Here we are just showing the tone. And the spectral display, data can be viewed in spectral domain, spectral amplitude on the left side versus frequency in the bottom in the spectral display. That's the frequency, and on the left side we have the amplitude. So this shows the spectral domain. Here we have pulse shape display, jitter measurement, and jitter generation. Pulse mask determines if the pulse shape fits within a pulse mask as specified in ITU standard G.703 and ANSI T1 102-1993. So we are showing a nice isolated pulse that's fitting in this mask. And the jitter measurement software measures jitter associated with an incoming T1 or E1 signal. That's the middle one, jitter measurement. And the last one we have is jitter generation, that is towards the right. That is used to test jitter transfer function. On the left side, we have this enhanced BERT. In the enhanced BERT option, you can choose both contiguous or non-contiguous time slots, channels, or even sub-channels. We can run framed BERT, unframed BERT, fractional BERT, sub-channel BERT. It supports a lot of BERT patterns, QRSs, 2 to the power 23 minus 1, all ones, all zeros, 2 to the power 9 minus 1, etc. Even CSU lookup down. So that is the BERT, enhanced BERT. You can see the results, both the results, if you click on the all cards at the same time, it is pattern sync or no pattern sync. On the right side, we have transmit signaling bits and signaling bits monitoring on the bottom. Here you can punch in any configuration of signaling bits from 0000 4 zeros to 1111. In the example here, we are transmitting 0101 on all the channels from 0 to 23, that is from channel 1 to 24. Since card 1 is connected to card 2, we are monitoring signaling bits on card 2. So 0101. You can change any of the signaling bits in any of the channels and you'll be able to see different signaling bits. This is the physical layer analysis. In this physical layer application, you can see loss of signal, loss of frame, AAS alarms, carrier loss, sync loss, blue alarm. This T1 alarms is in the real time. It converts them to SNMP messages, meaning simple network management protocol messages, and can be sent them to the NOC, that is the Network Operations Center. This on or off status in physical layer analyze says whether the alarm is there or not there, alarm or no alarm. And you can see all the layer 1 alarms, frequency, levels, and with the timestamps like system time, relative time, or the difference time. Right now what we have relative time. This is a good way to see the physical layer analysis, physical layer alarms, or any problems if you have on the line. This is ISDN protocol analysis. ISDN analyzer can capture and analyze stream of frames from an ISDN PRI link. I think we are showing ITU Q.931. It supports a lot of other protocols, ITUQ.931, ISDN ANSI, ATT4ESS, ATT5ESS, National ISDN. On the first pane, you see the summary view, setup, call proceeding. Second pane, you see the same detail view. Right now, we are showing the detail view of that setup. On the third pane, you see the hex dump view, hex dump data, hex data. Fourth pane, you see the statistics, like which device number and how many frames. And fifth pane shows the call trace. It shows the call status, whether the call is completed or it's processing. The third column shows the calling number, fourth one called number, and when it started with the date and time, and call duration. These calls look like very short calls, and why these calls were released, and where it happened, and where we are monitoring, and which time slot it happened, along with the CRV, that is the call reference value. So this is our ISDN protocol analyzer. Very, very useful application. In this, we are seeing the protocol identifier. This protocol identifier identifies various protocols carried on T1 E1 lines, protocols such as ISDN, HTLC, ATM, SS7, GSM, TRAV, I think TRAV are in some sub-channels, PPP, frame relay. See all of them here. Nice colorful display of all the protocols. On the right side, you see the SS1 analyzer and emulator. You can generate and analyze SS1/SS4 dial codes. They can be either 2-digit or 3-digit dial codes. We are showing the mark as 2600 Hertz, space 2400 Hertz. Looks like this one is a 3-digit because I see three of these, and looks like there is 888, digit 888. This is the SS1 display. Call capture analysis, multiple call capture analysis. This application monitors hundreds of calls based on CAS signaling or ISDN, SS7, fax, etc. And it can be triggered through signaling, tone, ISDN, SS7, or traffic. And you can limit time of recording. If you're not interested in the entire call, you can just say, like, I want to listen to only two minutes of the calls, just whatever you are interested in, or you can do unlimited capture of the calls. This application is very useful, like it gets triggered through different kinds of messages, such as ISDN message, SS7, or signaling, whatever you're CAS signaling, whatever you're interested in.
Okay, thank you, Shashi. So Shashi showed several slides about our monitoring and analysis capability. So now what I want to do over the next few slides is talk about our emulation capability. So what I'm showing here is our ISDN protocol emulation capability. This is related for those of you who know our message automation and protocol simulation software called MAPS. This is using that MAPS software in conjunction with the tProbe hardware to actually send out the ISDN call over the T1, over a time slot in the T1. So here on the left-hand side is a screenshot of us generating the ISDN call. You can see the whole ladder diagram showing the call setup and teardown. And this screenshot here on the right is the call reception side for the ISDN call. So we can place and answer ISDN calls over the T1 or E1 line. Again, it's a very nice, easy to use graphical user interface where you basically just click start and stop. You can configure all of the test parameters. There's profiles where you can set up all the ISDN configurations, calling number, called number. The calls are configurable in terms of audio. You can send and receive audio files, call duration, so on and so DTMF digits and so on and so forth. So again, this is using our MAPS software, our ISDN MAPS emulation software, in conjunction with the tProbe to place and answer the call. Here's another screenshot. This is now for GSM. Again, it looks and feels the exact same in terms of the graphical user interface. You start and stop the calls. Here on the left-hand side, we're showing a screenshot generating a GSM call. And on the right-hand side, we're showing a screenshot receiving that GSM call. For every single call, you can click on it, get more details on the call, whether the call was successful, failed, dropped, and so on and so forth. And let me show you one more example here. So not just over the T1E1, but we can also use the FXO FXS ports to send a conventional analog phone call. So we can go off hook, detect dial tone, dial DTMF digits, and so forth. So what you see here is being able to place a call just like an analog phone. So again, it's the same exact software, same exact look and feel. We see here that how the call is set up and disconnected, and so forth. So for all these various calls, we start them, we stop them, get the full analysis on what happened in the call. And the calls, again, are fully customizable. So these are just some examples of ISDN, GSM, FXO. For all these different telecom protocols, we can emulate the calls as well. So analysis and emulation. Okay, so moving on, Shashi, you can take over again and talk about our delay measurement capability.
Thanks, Vikram. This is precision delay measurement. This is part of the basic software. Precision delay measurement measures round trip delay. What do we have here? Loop back, outward loop back. Card number 2 is on outward loop, port number 2 is on outward loop back, and first one is no loop back. So we're going to measure precision delay measurement from port 1, and we have set port 2 to outward loop back. So outward driver loop back. This outward driver loop back simulates foreign loop back. So we are measuring the round trip delay as 11.4 milliseconds. You see that delay time on entire T1 0 to 23, that is channel 1 to 24 or time slot 0 to 23. We are seeing 11.4 milliseconds. So round trip delay is 11.4 milliseconds. So one-way delay is half of it, 5.7 milliseconds. We can measure delay in the network using this application. Next slide, please. This is showing another precision delay measurement. We are sending, on the right side, you see that error insertion application. We are sending a bulk delay of 50 milliseconds. On port 1, we are measuring the delay. So this is, again, we are seeing it as 50.1 milliseconds. It's pretty accurate. You may emulate delay by using several other applications that we have also using echo test delay and attenuate time slots. But this is just an example to show you how you can emulate delay and also measure delay. Next slide, please. This is the VF options. Here you see the PCM signal in a time slot is converted to analog and fed to the VF out jack. VF out, show the VF out, Vikram, please. I don't see the. That's in the bottom, VF out jack. And analog signal can also be fed to the VF in jack for insertion into any time slot. That is VF in on the top, VF transmit or VF in on the top. And there are speakers for both VF in and VF out, as you can see. And VF impedance can be set to 600 ohms. Right now we are showing 600 ohms or 900 ohms. High impedance, all the way the bottom, VF impedance. High impedance microphone. The analog data can be inserted into any T1 even time slots. You're already into dual VF. Okay. This application shows intrusive and non-intrusive VF audio monitoring and VF recording. Supports both SS1 or SS4 emulation and analysis. And also you see the 4 graphs. Visually you'll be able to see the spectral data, VF2, VF2 out, VF1 in receive, VF1 out transmit. You'll be able to see all the data, spectral data at the same time. And what else do we have? We can transmit VF and receive. We can record, receive file, transmit file, receive tone, transmit digits, and receive digits. This is a very useful application, dual VF transmit receive. Next slide, please. Here we are showing 2-wire FXO FXS. FXO port onto the right is used as telephone, FXO device such as telephone, and FXS port is used as a telephone wall jack. So we can simulate both FXO and FXS. Next slide, please. Here's a snapshot of all the T1E1 basic software. There are a lot of basic software, a lot of applications that come with basic software. All the line interface options, framing formats, clock, loopback, connections, encoding, bird testing. You see all this. I'm not going to go over, there are too many applications. So this is T1E1 basic software, list of T1E1 basic software. Next slide, please. Yeah, here is a list of special applications. If you have the basic software, any of these software can be enabled through software license. Supposing you just bought basic software, if you feel like, oh, I need ISDN analysis or emulation, you can add that license to that unit by buying that license. So contact us if you want to get details of any of these special applications that you are interested in. We have protocol analysis, emulation, a list of capture analysis, voice band analysis software, echo cancellation, all the emulation software, WCS modules, protocol identifier, multi-channel BERT, yeah, all this. Next slide, please. Now we come to this Datacom analyzer. This emulates both DTE and DCE in synchronous and asynchronous mode. Synchronous BER, we support from 300 bits per second to all the way to 16.384. Asynchronous, we support from 300 bits per second to 115.2 kbps. And supported line interfaces are, we have it here, X.21, V.35, RS port 422, 485, 530, 232. Sync clock source and frequency measurement. So we can emulate both DTE and DCE. Next slide, please. We can emulate DTE. As you can see, DTE, like data terminal equipment, it's an initiator or a controller, like routers, computers, printers, file servers. And DCE is the data communications equipment, the device connected to DTE, such as modem, DSU, CSU, or multiplexers. DTE, DCE emulation for end-to-end testing of data networks. So you can see here, you can do DTE, DCE emulation for end-to-end testing. And we are also showing the monitoring of Datacom lines. And in the bottom, you see the frequency 16383928 on both DTE and DCE, port 1, port 2. Next slide, please. This is bird testing in Datacom. This generates and detects data. Right now we are showing the QRSS pattern. And the other bird patterns, as I explained before, are QRSS, 2 to the power of 6 minus 1, 2 to the power of 9 minus 1, 2 to the power of 11 minus 1, 15 minus 1, 2 to the power of 20 minus 1, CSU loop up down, NIU loop up down, all ones, all zeros, a lot of them. We may insert errors, see the statistics, time, and on the left side you see status errors, total errors, error rate, and available seconds is our total seconds. And you may insert errors, the bottom, insert single error, insert. So this bird application, it tells you, right now it's showing path sync, that means it's receiving the pattern that it's sending. QRSS, we're sending QRSS and receiving. So everything looks good. Next slide, please.
Okay, thank you, Shashi. So, yeah, the final slides I want to emphasize our Python scripting capability. As mentioned, a lot of customers are starting to ask for this. So basically, through Python scripts, you can fully control the tProbe. We provide sample scripts, and the way it works is that the tProbe is connected to the Windows PC through the USB connection, just like before. But now, instead of invoking the graphical user interface, you run a, sorry, my mouse sometimes disappears there. You run a background server, CLI server, command line interface server. And that server listens to commands coming from the network or from the same PC, basically TCP/IP commands. And you can then, from the convenience of any PC on the network, Windows or Linux, you can run a Python script to connect to that server and then therefore fully control the tProbe hardware. So that Python script can run on the PC directly connected to the tProbe, or it can run on a PC elsewhere on the LAN that can and can talk to that Windows PC, the CLI server. The Python scripts are very easy actually to use. When you look at a sample script, it's pretty intuitive. Even if you don't know Python, it's very easy to just modify a sample script. to do what you want it to do. We also provide an API manual and so forth. So the advantage of the scripting is that you can run tests repetitively in an automated fashion. If you want to run hundreds and hundreds of tests, you don't want to have to click buttons on a graphical user interface. You would rather just put it all in a script and put it all in a loop, and off you go. So that's what you can do with Python scripts. You can also control multiple tProbes through Python scripts. So it makes life a lot easier for you. Here's just some snapshots of a Python script running. We don't have to talk too much about all this stuff, but again, we provide sample scripts. It'll basically spit out all the results to the Python shell. You can also export all the results to a text file, just like you can basically do anything through this Python script, right? So all of the results are available to you in real time, and you can simply export them to a text file and then graph it with whatever graphing software you wish. So that's a little bit, just a quick snapshot of a Python script. Thank you all very, very much for attending this webinar. If you haven't already, by the way, please subscribe to our newsletter, where we routinely put out new features and functions about our tProbe and other hardware devices. Thank you all very much. You can also email us at info@gl.com if you have further questions or would like to see a full web demonstration of the tProbe. Thank you all. Enjoy the rest of your day.